great graduate student with Alex Quinlan down in Rochester, and he just recently moved to Potsdam, and he's going to talk about some of the work he's been doing on galactic dynamics. So,
thank you very much. Very happy to be here. I'll talk to you about the internal processes in galactic disks that will shape the disk and contribute to disk evolution. And this is mostly done by a central bar. The Milky Way has, this is actually a cartoon of what our Milky Way looks like, supposedly, and spiral structure in the outer disk. Those are density waves propagating through the disk. And I'll show what the implications of those two patterns could be in the general context of galaxy evolution and also apply to the Milky Way. So first, show you what we think galaxies are the main component of the galaxy. This is in the case of the Milky Way, but that's what most galaxies should look like. This is there's a dark halo where most of the mass is contained, 95%. We have a stellar halo, shown by the yellow here, yellow color. Then we have a thick disk and a thin disk. All the rotation is supporting components. In the center we have a bulge, which is a pressure supported component. Bulges come in different sizes. Could be primordial, meaning that they formed as a galaxy form, or they could be pseudo-bulges lifted up by the bar. We believe in the Milky Way the bulge is quite small, maybe not even a real bulge, but just a pseudo-bulge lifted by the bar. That's the latest Brown survey study shows. So, very important here, this is the purpose of my work in this talk, we need to understand how galaxies behave in isolation before we can include the effect of mergers in the full cosmological context. So here I'm just going to talk about the effect of the internal perturbers on the disk evolution. And then once we understand those, we can include mergers and stuff like that. Some galactic disk properties. 2/3 of all disk galaxies have central bars that I'll show. Those are very important for disk evolution. They stir the disk, create resonance structures, and all those galaxies also have spirals in addition to the bars, because bars drive spiral structure. So you can't just have a bar, but you also have spiral structure in addition to that. Thick disks are ubiquitous in all size systems, and also extended disk profiles lately have been seen in many galaxies. I'll show you in a second what thick disks and extended disks look like. And just to point out, although we can simulate, it seems like cosmological simulations give good predictions for halos and so forth, we still have big problems creating disks in cosmological simulations. So I'm not going to show anything done in that context, but just isolated cases. So this is an observed thick disk. This is the thin disk. The longer exposure here shows a thicker component. It's fainter, but it's there if you observe longer. So we believe the Milky Way has a thick disk as well. What are extended disks? Standard example here is Angelston 300, where it's been seen that the surface density as a function of radius, this is the brightness, which is also something like the surface density, it extends exponentially all the way to 10 skelets or more. So it just keeps going. This is very interesting because many galaxies, disks are truncated, so you'll see a drop right here. This keeps going. And I'll show that these can be explained, at least to some extent, by internal instability of the disk. So what do we want to know about the Milky Way disk? To understand the Milky Way formation and evolution, we need to know its current morphology, dynamics and kinematics. The thing is that we only have a snapshot now and we have no idea what happened in the past. And hopefully from the kinematics and the distributions we would somehow recover its past history. In the case of spiral structure in the Milky Way, which is very badly constrained, we don't know the number of spiral arms, we don't know the pitch angle or how tightly they're wound, we don't know if they're transient or short-lived. Transients will be appearing and disappearing on a rotation timescale. A long-lived will survive for longer times, giga-years, for example. In the case of bars, even though the central bar of the Milky Way is much better constrained, we still have many questions. Is it slowing down or speeding up? Does its strength vary with time, for example? That will have consequences on the disk. And here are some questions pertinent to both spiral and bar. Angular velocity with respect to the background disk. Orientation with respect to the sun. And what about the strength? Strength is very important. Also, the stronger perturbers will perturb the galaxy stronger. Okay. So this is a non-bar galaxy. An example, in case you haven't seen, this is a bar galaxy, very strongly bar galaxy. And as I said, there's also spiral structure in addition to the bar. So the talk outline is as follows. I discussed 4 topics: radial migration in galactic disks, resonance moving groups in the solar neighborhood, velocity distribution. Then I'll go to a more complicated case of multiple patterns in galactic disks. And finally, small-scale space structure in these more complicated n-body models. So first I'll just briefly talk about resonances because those are very important for the evolution of the disk. So here the thing is that disks rotate differentially, meaning that the central parts rotate faster than the outer parts because the rotation curve is flat, so the velocity is constant with radius. Here you one revolution is faster than the outer parts. Now we can get, let me show you. There you go. So if a monkey pushes on a pendulum like that, at one point exactly at the right time, at one point the monkey has peaked out. Here, the bar and the spiral structure of the monkey, then it starts with the pendula. So we have, this is supposedly the sun, the bar is going faster than the sun, so it's overtaking the sun. Spiral structure is usually moving slower, so the sun is overtaking the spiral structure. The faster the perturber moves, the more inward the resonance is happening. And this is because the bar and spiral structure density wave, they move as rigid bodies, and this is differential. So there is a particular radius for which the bar and the stars move at the same speed. That's called the corotation, shown as the dotted circle here. But if the perturber moves more slowly, the corotation moves outwards. Okay? Then we have an inland resonance, shown by the dashed circle, and the outward resonance. So we get periodic kicks every time the star goes around. And here, the outer inland resonance lies outside the galaxy, so I haven't shown this is the inland resonance. And it's very important that bars rotate faster than the spirals, so the resonance is happening at different radii, and this resonance overlap will have strong effects on the disk evolution, as I'll show. Here we're going to the first topic, radial migration in galactic disks. This has been given a lot of attention lately, and I've done some work in it. Why do we care about it? This was invoked in the context of the age-metallicity relation in the solar neighborhood. It's been observed that classical chemical evolution models predict the metallicity gradient age with age in a particular radius, but it's been observed. This is in Hipparcos data, Geneva Copenhagen survey. This is the metallicity, the function of age. You don't really see a gradient here, pretty much flat. More importantly, there's this huge scatter around it. So this means that stars from the inner and outer radii are somehow getting to the solar neighborhood and polluting our sample. How can this happen? You have stars that are more metal-rich in the center and more metal for the outer parts. If they somehow change their angular momentum and ended up in the solar neighborhood, it will create this scatter. And this is what we mean by radial migration. Not just the eccentricity change of the orbit and reaching the sun, but also just changing angular momentum and still being on a circular orbit. So you can start with a circular orbit, end up on a circular orbit in the outer disk. You need a change in angular momentum for that. Different disk mixing mechanisms. The first one invoked by Selwood in the context of this age-metallicity relation is by transient spirals. This requires that we have short transients on the orbital time scale. Then recently we have done some work with Alice Quillen here on small satellites. We showed that small satellites can mix the outer disk. And most recently here I've done two works on resonance overlap of multiple patterns that proves to be an extremely efficient mechanism for any bar galaxy. Now we're going to talk first about the radial migration and the corotation of the bar or spiral structure. This is test particle simulations. I'm showing here a cartoon of the bar model, spiral structure model. Test particle simulations mean that the particles don't feel the gravitational force from each other. They just respond to an imposed potential. And have full control over the simulation parameters, such as the bar pattern speed and strength, and the spiral structure pattern speed and strength. So here I'm showing the change in angular momentum. This is the initial angular momentum versus the change in angular momentum. The initial angular momentum is something like the radius is divided by the rotation speed. So this is 8 is like 8 kiloparsecs. The sun is around here. And then simulation with the bar. This is showing the outer resonance of the bar, which we believe is just inside the solar circle. The corotation is the dotted line again in the inner and outer circle. Similar to the spiral here. This is the corotation. And as you can see, there is a change. Delta L changes here only around the corotation. Inside the corotation stars are gaining angular momentum, meaning that they're shifted outwards. Outside the corotation stars are losing angular momentum. So there's this swap across the corotation where the surface density is roughly preserved. And it's similar to in the case of the spiral. And this is all the effect you get. There's no variation with time. This is not nearly enough to explain observations. If we believe them, we're going to challenge that later. So, this is why we need transient spirals. This is a cartoon way of showing you how this figure results. This is from several Vini and body simulations. The change in angular momentum again versus initial angular momentum. Say its radius, 20 kiloparsecs. This is the center of the galaxy. This is 0. So you see that there are these prominent ridges over there. The strongest happen around here, about 2 scale lengths. And the reason is that you will develop stronger spiral arms. You will use stronger effects at about 2-3 scale lengths, where the Numerical parameter is the lowest, which depends on the velocity dispersion and on the density. As you go in, velocity dispersion increases, so the spirals become less prominent. In the outer galaxy, the density decreases, so Numerical parameter again decreases. So you have smaller effects. So how this works is, this is one corotation I'm showing, and you have this effect that is just described. If you happen to have transients happening randomly, as in the theory of Selwood, they will cover the whole disk with different strength perturbers because of this Numerical parameter cube. It will happen like this randomly. Stronger effects over here, and you get something like that. Very simple. Effect of transit. This is great. It explains the observed age-metallicity relation. It requires 90 years for sufficient mixing. Now, since the Milky Way has also a central bar, and the transient spiral simulation did not include the bar, we wanted to see what happens if we include that effect of the bar. So with the test particle simulations, they showed before, where the effect of the bar is this, the effect of the spiral is that. If you put the two together, do a simulation like this, with both bar and spiral, and that's how the resonances are situated, the resonance radii, actually. You do exactly the same parameters, just perturb the disk by both bar and spiral. You see what happens. And this is the effect you get at the very beginning. It's a function of time. At the beginning, you have just the linear superposition of the corotation radii of bar and spiral. Very quickly, this is a half a gigayear. You have strong effects happening in the middle here, and also the corotation radii effect is reinforced. And only in about 2 gigayears, you have this huge mixing. It starts from different radii moving around. You see here very strong bimodality, which which is the signature of this mechanism, because the strongest bar resonance is the outer limb of resonance, given by the red line over here. And any other resonance due to the spiral in combination with that would be the strong effect. I'm not going to go describing now why this happens, but near resonance overlapping at the chaotic regions, stars are being scattered, heated, and migrating at the same time.
So the scatter normally radial, you also find any?
It's very interesting because in the z direction, so in the inner parts, we have high velocity dispersion in the z direction. So if you scatter stars outwards, you can imagine that they will keep their velocity dispersion in the z direction, so they will keep the disk outwards. Create like a thick disk component just because they're migrating outwards. So this mostly works in the disk, yes, in the plane. But because it's carrying stars which already have high velocity dispersion in the z direction, you can also keep in the z direction the whole disk. It will also scatter some bulk stars through the ship cloud. And then we went ahead, no one believed this test particle simulation case. So we looked at the fully self-consistent n-body SPH, star formation, gas, everything. So here is the Galileo database, which is available online. These simulations are not designed for radial migration or anything. We just looked at to see what happens in 3 different kinds of simulation setups. So this is the time evolution of the changes in angular momentum for one of those SA galaxy type from the Galileo database. You see at the very beginning here, as soon as the bar forms, you have a peak near the corotation and another peak forming near the outer limb of resonance. And that is the signature that we expect to see from the test particle simulation. That is prominent all the way to 3 degrees, but the whole thing takes actually shorter time even than we expect with the test particle simulation. It's extremely effective. In 0.8 gigayears, we mix with this completely, erase all signatures, create a thicker component, extend the disk, and I'm going to show you.
Sorry, is the angular momentum gain and loss more or less balance out to 0, or is it just a net change in angular momentum?
I'm sorry, I don't understand.
You're showing those radial hours.
So this is binned in radial bins, and plotting in each radial bin how much. This is the initial angular momentum, and this is showing over here how much the stars, how much angular momentum has changed of the stars in that particular bin. Yeah, so there's a positive. The current is different. It's positive inside the corotation, negative outside the corotation. So there's a swapping. But then, of course, also be shifted back to the in and out.
So it's a net inside of 0, meaning you're not.
Oh, is it? Right. So the point is that the disks are, the density is exponential, so you have more stars inside. So even though it seems like you have the same effect in and out, you're actually shifting more stars outwards. You extend it to this. You start with a particular rate.
Something has to go in there. Who's going in?
It's just the redistribution.
Some stars have to be shifted in.
Yeah, some are shifted in, but more are shifted outwards.
So if you apply your own perturbation, then you can magnify it towards the whole system. But if not, then something has to take up the balance.
Or there's an exchange also with the halo. The bar is slowing down. So the bar loses angular momentum to just initially form bar. It slows down and weakens because stars from the bar escaping. Yeah, it's more complicated than what I'm showing you. But
So does it say cold, like these
keeps
stars
up.
migrate, they has large radial velocities, right?
Yeah, the last dispersion increases.
Okay.
Yeah.
So that's a difference from basically Selwyn Ping-pong where they.
No, they also they have a paper on heating of galactic disks by transient spirals, and they have a paper of mixing the disk without heating it.
Right, yeah, that's the thing I remember is mixing
So
this
the
one.
thing is that across the corotation,
Yeah.
you have change in angular momentum without heating.
Right.
But since spirals end in inner and outer limb of resonance, that's where it gets strong heating. And if those are happening everywhere in the disk at random places, you expect heating everywhere in the disk. Right? From the inner and outer limb of resonance, but at corotation you have this nice exchange. So it's in a way it's similar. Right. Although it's more uniform than this you would expect structure with radius. So here is another simulation. This is the Geneva group code. It's a particle mesh. And here we actually looked at a much higher resolution with 10 million particles in the disk compared to this 127K particles in the disk, and we have exactly the same effect. So this is not effect at low resolution. And finally here, 5-grade pure n-body simulation on GPU cluster. We did this very recently without a spoon. This is not really showing the bimodality because there are many multiple patterns propagated with this. I'll talk about the simulation later. Here just to see how much mixing happens in the disk. I'm showing the distribution of home radii at 2 gigayears of particles starting in the range indicated by the green lines. Here at about 4 kiloparsecs start between the green lines and they end up where the histograms show. The red one is the total population and the black one is just the ones in circular orbits. So you can separate this into circular and up orbits. This is showing at 6 kiloparsecs, 8 and 10 kiloparsecs. This is for a different combination of pattern speed of the Barton spiral structure. And just to compare this to the transient spirals, this is the x-axis is to scale. You see the same width here, except we do it in 2 gigayears instead of 9 gigayears. So this could be an order of magnitude more efficient than the transient spirals. So some implications of radial migration, more specifically this time with the bar included. Here I'm showing the SA model of the Almaer database. This is the initial setup, the function of time. You see that the initial tinges thickens quite strongly. This is the age on view, face on view. You see that the disk extends at the same time. Here I'm showing the vertical velocity dispersion, where the dashed line shows the initial. Just look compared to you can see it. But you can see that the disk extends and also pops up without flaring, which is a problem for creating thick disks by mergers. We usually flare them. That's not observed. We don't want to flare them. So, looking at the vertical scale height, initially 300 parsecs, which is the new for a thin disk. So this looks like a thin disk that we start with. That is gradually thickened, and at one point, function of time again, at one point you can fit this by 2 exponentials. And here the exponential scale heights are exactly what the Milky Way is supposed to be. So it seems like we can produce a thin and thick disk out of the initial
so the vertical scatter, the vertical peak is just used
due to the redistribution.
small star, like the central star being reached the outer
Yes.
one. So there's no intrinsic peak in the disk that you are talking about.
There is also, in addition to there is some.
Or really from that one, the spiral.
Well, we would expect that the bar, in a fully self-consistent 10-body simulation, have the bar and the spiral, they will never be perfectly aligned. So they're wobbling like this. But resonance, they will scatter off into
I'm
the direction.
just think you're arguing for a vertical oscillation.
Yes.
Is the vertical, the vertical velocity dispersion, is that, what is being conserved? Is the angular momentum in that velocity component that's being conserved, or is the velocity being conserved?
The angular momentum, the total angular momentum is conserved. Some of it actually losing, the disk is losing angular momentum to the halo. And is the velocity conserved? The velocity, what do you mean by that?
Well, you're saying it's thicker, not thicker on the outside, because the higher velocity spread will moving out. But as it's moving out, it is conserving the momentum.
There is a, so energy and angular momentum are not really conserved. There's an exchange between them. There's a conserved quantity in the case of one perturber, which is a Jacobian. But even that is not conserved in the case of having 2 perturbers, bar and spiral. So actually, I'm not going to go into this now because I don't have time, but as stars migrate, they start with 100 kilometers per second velocity dispersion in the inner disk. They go out and the velocity dispersion drops. So that particular sample, the stars are losing velocity dispersion. Yes. So there's this redistribution where the disk is kept, the scale height of the disk is kept constant. The ones that move in gain velocity dispersion, the ones that move out lose velocity dispersion in the direction. So this looks like we can create thick disks, except we can't. because then when we decompose this into a disk and a bulge, this is what I just showed you. That looks like a thin and a thick disk. This is from the disk and a bulge. You just look at what happens to the disk. You see that we start with 300 parsecs, end up with almost double that, 600 parsecs. Not enough for a thick disk of the Milky Way. And if you look at the bulge, you see that this contribution here actually comes from the bulge, which is fine. Maybe we can just scatter stars from the bulge and create a thick disk, but that's not really the case. Here we have the SA model. For the Milky Way, we hardly have a bulge. This is an SA model with a huge bulge, and even in this case, even for the strongest bars, the contribution from the bulge is only up to 2 disk scale rates. So if we look at the solar position, solar radius, we would see something that looks like a thick disk, but we don't see it any further. So actually, I don't believe that this is the strongest bar in the Gaussian database. But to me, it seems like we cannot do this with the one.
So why is that? Why is it bulge? Why is it all the why is all the scattering from the bulge not the same radius?
No, there is scattering from the disk also.
So it's much weaker.
But it just doesn't carry the radial the vertical velocity. As stars are moving out, they lose velocity dispersion. But those from the bulge, which are which have very high velocity dispersion, will still reach with the required amount of the thickness. Well, this is still good. We can double very quickly in 1 gigayear. We can double the scale height, and that would make the disk less responsive to mergers. Thus, we don't really flare it. So even if we have this at the early stages of evolution, we can thicken the disk, and then, since we expect to have effective mergers, we know mergers do exist, we would expect some heating from them. But we're not going to really flare it because the disk will be less responsive since it's already thickened. Now, another implication of radial migration is extended disks. As I showed earlier, any extended disks have been observed. Here I'm showing the surface density in logarithmic scale versus the radius. The dotted line is the scale length. The red line is the truncated initial disk. And then those lines show consecutively the increase with time. In the end of 3 gigayears, we have almost an exponential extension up to 10 scale lengths. This is for the case of S0, no gas. And looking here at the metallicity distribution of the function of radius, this is the initial distribution. You see that the disks are flattened very quickly. And even there's this upturn here, which is also observed in galaxies. And if you just track this, the height, that's the metallicity, you can tell that these stars came from over here, which is what, 8 kiloparsecs. They travel all the way out to about 40 kiloparsecs. Very interesting. This is the Fourier decomposition of the A2 component, which will show this is the central bar. This shows the strength of the bar, the height here. This shows the extent. This thing is the bar. The extent right here is around 5 kiloparsecs. And this is the spiral structure strength. Now this is the identical simulation setup, except you have 10% gas. You see the spiral structure is much stronger here because the gas pulls the disk, so we have lower 200 grams per cube. Even though the bar is weaker than in this case, we have stronger effects, slightly stronger than that, because of this resonance overlap of the bar and spiral resonances. Now this is an SD galaxy with 20% gas. This is something like the Milky Way. The bar is much weaker, spiral structure much weaker. We hardly have any extension. Maybe the Milky Way does not have an extended disk. Of course, we don't know the past history. Maybe we had a huge bar in the beginning, and now the bar is much weaker. And finally, this is an SD, no bulge, no bar, but there are multiple spirals. You can see this craziness here. Multiple spirals propagating through the disk, again, this extension. So we concluded from this that any multiple patterns will create these effects. It doesn't have to be a bar and spiral, only to be multiple spirals. But as I'm going to show later, even in the Milky Way, we may have a bar and 2 different patterns moving at two different spiral patterns moving at different pattern speeds.
So why is that 20% gas going to get a deeper spiral? Because you have more cooling.
Right, yeah. It should be stronger.
Yeah.
You don't know. You put it's an inverse relation, put things in, and then you don't know what's going to come out.
But the bar was weaker in this case. You're saying.
The bar, yeah, the bar is weaker.
That was sure.
No,
So you say that maybe
spiral is just basically.
well, the bars can form spontaneously. They don't necessarily need the bar. You're saying that the bar may, because it's weaker, it doesn't drive strong spirals? Or?
Well, so we're sort of saying the bar is an important driving mechanism.
It could be, but there are different mechanisms of creating spiral structure. They can.
But there's some dominant compared to the bar. It looks like from your results, right?
The what? The dominant result?
The effectiveness of these transient spirals.
I thought they were look at the.
No, you don't know exactly whether this is self-generated or is bar driven. It seems
The
like.
second row seems very similar to the first row, right?
Well, you have a strong bar, but the spiral structure is still weak, right?
So what's the result I should be looking at here?
But the result is that to start with a truncated disk and it extends very quickly, it has the effect of having both bars of spirals.
Okay.
And it seems like when
And so if you turn off the bar, which is like the third row, like the effect.
the thing is that here there's always multiple catalysts. But here, because the strength are weaker, you don't get so much. This is the only one that you don't quite get the same.
That one you have the bar on spiral. The last.
All right, I guess what this should tell you is that
No,
this.
no, the SV case has no bar, you were saying, right?
No, there is a bar, just
Yeah.
weaker.
That's no spiral. That's the
Yeah.
right one, right?
And they're weaker, so the effect of this resonance overlap is non-linear, very strongly dependent on the perturbation, how strong the bar and spirals are. So there is some turn off here. If you make this a little bit stronger, it will have a much stronger effect on the migration. Not really quantified yet. So how can this? This is a problem for galactic archaeology. This is Ken Friedman is very much involved in this galactic archaeology. I'm actually in the galactic archaeology group, and Potsdam just recently joined. And this is the definition. We seek signatures or fossils from the epoch of galaxy assembly to give us insight about the processes that took place at the galaxy forum. Well, now in view of the last two slides I showed you where this mixing is so strong in just 1 degree we can erase all signatures, we flatten it, just gradients. How do we look for these signatures? So I was just at this conference in Potsdam. I illustrated this by this picture, this problem we have. This is galactic archaeology, it's radial migration. This was just 2 days before I joined the galactic archaeology group. Maybe this doesn't really work in the Milky Way, right? Things would still be okay for the Milky Way, and you still get galactic archaeology going. So let's look at some problems with the age-metallicity relation, age-velocity relation in the Geneva-Copenhagen survey. This is the Hipparcos data by Geneva-Copenhagen, people, distances, and ages. Again, metallicity is a function of age, huge scatter, no gradient. This is the velocity dispersions, radial and tangential. It's a function of age again. Logarithmic scale, so this is the power law. This is what they predict. Both of these trends are explained by transient spirals. But if scattering the age-metallicity relation is found to be small, then models of short-lived spirals become problematic. And here we have these questions here. Do we really believe the ages? And the answer is no, because the Geneva-Copenhagen survey published their first paper, the Geneva-Copenhagen, the second one, the third one was just the Copenhagen. So the Geneva people, they wrote a paper that the ages are all wrong. The Copenhagen people didn't listen. And you see here the errors of velocities, there are no errors in ages. That's because they don't fit on the clock. And so probably we have problems with the ages. There is a paper that shows the ages. So,
How do you have a mistake in ages between, let's say, 10 millimeters and 100 millimeters for the stars?
there's some bias. I don't know if that's. There's a. So Ken Friedman actually has a student working on this. This is a plot. This is 20-year-old survey, 200 stars only, 70 times less than the general Copenhagen survey. But Ken Freeman has been showing this for many years now. Velocity dispersion, radial velocity dispersion, tangential, and in the z direction as a function of age. So there's this heating saturates about 3 gigayears over here before the green line. There's an increase from internal instabilities. And then he claims there's a plateau here. This saturates, the heating saturates. And all of a sudden in 10 gigayears there's a huge burst, which could be due to a merger, for example. Right? So Ken was saying that 200 stars only, but the ages are very accurate. So the number doesn't matter. The error in the ages matters. Because the student was working on 300 stars, getting very accurate ages, and it seems like there's a very small scatter in the age consideration. And also there is no power over it, it's more like this. So at that conference, this is the slide that Ken showed after my talk. Well, the thing with the resonance overlap migration is that we have full control. As long as we can control the strength of the perturbers, which we expect them to be stronger soon after formation of the galaxy, because the disk is too cold. We have strong instabilities, about 1 to 2 gigayears to heat the disk to scatter stars, and then the effect becomes small. So before the first 10 gigayears ago, we have this huge effect, and we have strong increase in the age-velocity relation, and then a plateau. So this could work. We have to find the proper model for all the lifetime of the galaxy. How can we constrain radial migration rates in the Milky Way? Important question right now. You can look for variations in the density and the density distribution at different locations in the galaxy, since that's what we predict should happen in different ways. The resonances are closer to each other, we have stronger effect in other places. This can be done with rate Gaia apogee. The most promising is the chemical tagging. It's proposed by Ken and Jocelyn Hawthorne. We can observe, we can get measurements of about 35 elements, 7 to 9 dimensional space. Some of those will give you the same dimension. But the sole star cluster then will be a point in chemical space. So we scan the galaxy and then record all those elements, and all the stars will be saved that will appear a point there. Will be a cluster that can be solved. So by looking at the rate of variation of those stars scattered, we will know, and also knowing the time, the ages of those stars, we will know in a certain amount of time how much that was spread. So that will be the rate of migration. We can require that models be consistent with the velocity dispersion observed today. Very important here, velocity dispersion near the sun may be an underestimate because we are between spiral arms, and we usually behave like this is the velocity dispersion at that radius, but the velocity dispersion may be a function of azimuth, as I'm going to show. And finally, does the Milky Way have an extended disk? You can answer this question with the extensions to Hipparcos and the Moss. I'll move to the next topic, which is resonance moving groups in the solar neighborhood. This is the UV plane. This is the galactic disk. Position of the sun, galactic center, 8 kiloparsecs. Very interestingly, this is the Hipparcos here, kind of to scale. So from the velocities and positions of those stars right there, we're trying to draw conclusions about this, about the spiral structure, about the bar. We're embedded in the disk, so we don't know the morphology, right? We don't even know how many spirals we have, orientation or anything. So if you plot the velocity, this is the radial velocity and tangential velocity, galactocentric, of stars in the sphere, you get something like this. Right in the center, 0, 0, will mean the star is moving a perfect circle. As you go around, stars will be oscillating. Right? So if everything is symmetric, things will look like this. This asymmetric drift is because stars, there's high velocity dispersion in the inner parts, so stars in the inner parts are polluting the sample around the sun. So we have this weight for negative velocities. Now observationally, you see that this is the UV plane. It doesn't look smooth, which means that the disk is not axisymmetric, unless all these are dissolved in clusters. But it's been shown that most prominent low velocity moving groups in the solar neighborhood, Camel Berenices, Sirius, Pleiades, Hyades have dynamical origin because they have they're mixes of different ages and metallicity. They can be solved and they're quite old stars. So they can be created near resonances with bar and spiral structure, and thus we can constrain pattern speed. If you know where the resonances happen, as I showed earlier, that will tell the pattern speed of the bar spiral. So the bar is going faster, then the resonance circle will be more inward than out. So if you know where the resonance circle is, you know what the pattern speed of the circle. I've done some work on this. I'm going to show you here. This was work with Alex, Will, and Eileen. So here we show that for a likely position for the sun, just inside on the spiral arms, so a two-arm spiral structure, and just outside the 4-to-1 Lindblad resonance. So position right there, you will get two families of orbits crossing the solar neighborhood and puncturing two poles here in the velocity space. Imagine there is a group of trapped orbits around this line and another one around this star. They will appear as streams over here. Now, I was inspired by this and tried to see what the bar can produce. So I did simulations with the bar only, test particle simulations. Now the thing is, you have one perturber only. You expect that you will have no time evolution of phase space. So you don't expect, as soon as the bar is formed, you don't expect structure in the velocity space, for example, to change with time. What I notice here, this is a function of time, like this. This is the initial axisymmetric disk. The bar is growing, the bar is fully grown, and then you see a clump here streaming out of the central clump. And then slightly later on, there's another one streaming toward negative radial velocities, going farther and farther, and then disappearing, then the process recurs. These lines here are showing the recurrence of those streams, and because the slopes are not identical, it means that this stream here has a different recurrence time. So I wonder what this is, and by staring at this for a couple of weeks and checking my energy conservation, I decided to plot the actual orbits. So this is exactly the same time steps. This is the galactic bar here. The corotation is the dotted line. The alpha resonance is over here. And I put a ring of stars, 1,000 stars, very close to the resonance to see what happens to those stars. This black dot is the solar neighborhood, the side of the solar neighborhood. So here, the bar is grown fully. And then you see that so these are color-coded. In the inner part, they're blue, and the outer part, they're red. So they go from blue to red. So you see very shortly after the bar is grown, you have these two families. It seems like they're precessing, going around like this. There's an offset between the blue and the red orbits. And this is much better seen in the movie, which I don't have, but I have a cartoon here. You expect these are called X11 and X12 orbits. It's been described by Fuchs and Damien. So we know about these, that inside the dot, the dash circle is the resonance. Just inside the resonance, we have orbits that are going against the bar, and just outside, there's an orbit supporting the bar. This happens across every resonance. You can get these two types of orbits. So this is what happens. Those are supposed to be stationary in the reference frame of the bar. But what happens in my simulation is that they actually precess. And in particular times, both of them will cross the solar neighborhood. Right? It's like right now, they cross the solar neighborhood. That's why you will see them streaming in UV plane. You will see those streams coming out. And we interpreted this as the effect of, so the bar is fully grown, but the disk takes some time to respond to the bar. And these oscillations damp, and at one point they became stable. In the reference frame, the bars don't move anymore. Okay? So looking at doing parameter sweeps, and changing the pattern speed this way, angle this way, to get UV plots, see what happens. You see as you change the pattern speed, those clumps move to more negative velocities because this is near the near the resonance. As you move away from the resonance outwards, it takes longer distance for those orbits to travel. and that's why they appear lower in V. They have lower angular momentum. So the colors here are plotting the angular momentum. So blue corresponds to loss in angular momentum. And another one is you change the angle. So this is the major axis of the bar with respect to the sun's electrocentric distance. You see that now this clock moves with respect to the radial velocity. So you can imagine that if you match this, for example, this is matched to the observed UV plane, you measure the position of that, you can constrain the angle on the pattern. Right? And at the same time, you can constrain also the time of formation of the bar with this particular model. So that's what we did here. This is the observed Hipparcos distribution. This is from the simulations for this particular time of 8 rotations of the sun. Angle of 25 degrees and pattern speed. We can reproduce the series in Pleiades. Now for different time and angle we can reproduce the count variances in Pleiades. And those come from these ortho families.
So, I have a question about this effect you're describing. If you start the orbit not circular and then turn on the bar gradually, but turn on the bar and then let them settle into cold orbit.
Let them settle in what?
Cold orbit.
In cold orbit.
In response to the potential of the bar as well. Then you wouldn't have any of this effect you're talking about, right?
But there will always be a subsample that is trapped in the bar resonance.
But they are, okay, we can talk about it later.
Okay. So what I was showing before was just simulating a cold disk, but if you include hotter population as well, you also get here, this is the Hipparcos stream over there that comes for free. Okay, so that's been known that the Hipparcos stream can be reproduced with the bar. So from this, I constrained the bar orientation by 30 and 45 degrees, which is a very nice estimate, and it's consistent with all the estimates done by completely different means. The pattern speed was very well constrained as well, also consistent with other estimates. Bar formation time here 2 years ago. Okay, so what's next? See what the spiral structure does. I did this for this paper from Radial 2010, and it seems like the spiral can explain the Hyades and the Sirius. Those are the two groups that we can't really explain with the bar. A particular pattern speed of spiral and angle, consistent with what's observed. So we have this. We expect the combined effect bar and spiral. From spiral structure we get this. From bar we get that. We explain the 5 major components. Of course, these are very simple models. Dynamics will be much more complicated than in this part. Okay. How much more complicated? So here we're going to look at an n-body simulation that they said we recently did with Alice Quillen on the GPU cluster. We'll talk about multiple patterns. And this is the time step snapshots of the simulation. Very interestingly, you can see this looks like a 2-arm structure. At certain times, this looks like a 3-arm structure. There's one that looks like a 4-arm. Right now. So at different snapshots, this thing looks like different galaxies, which will tell you that there are multiple patterns going, interfering with each other, and so forth. Here, these are snapshots for a galactic angle with respect to radius. This is a different way to see these plots. This thing corresponds to the bar. This is one end of the bar, the other end of the bar, and these are spirals. This is plotted logarithmically. So here, a line will give you the pitch angle or the winding angle of the spiral at different times. Yeah, they say that galactic initial conditions for the galactic ICs from which our Induced model, those are the best initial conditions for Milky Way galaxy. So here we're plotting on these particles. Halo is live, center of the bulge seems to move. And there's a movie. At different times, different things happening. Then the bar is fully formed. You see the spirals are changing, but it looks like a real galaxy, more or less.
So this is actually rather strong one, right?
Quite strong, yeah, it's stronger than the Milky Way. The Milky Way is like 4 kilopascals, this is like 5, 5.5.
No, in terms of the symmetry, the Milky Way is like 5%, 10% bar strength. What's this bar strength?
The bar strength, well, the bar strength depends on the ratio of the axis, not just how heavy it is.
Yeah.
But it's, if you put it in this QT parameter, which Francois Combe uses, it's 3.5, and the strongest ones are about 4.5. So it's definitely not a really strong bar, but it's not weak either. And this is the same movement, but in these polar coordinates. You see here that the bar moves much faster than the spirals. And then you see that there's some constructive and destructive interference between the patterns. You see those gaps everywhere. Very interestingly, despite its localized density peaks, the galaxy still looks like a spiral galaxy. Here, the axisymmetric background is subtracted. That's why you see this so well. Right? Very interesting. No one has shown this with the background subtracted to exhibit the spiral structure so nicely. So let's see what kind of patterns we have. This is the power spectrum versus radius here. So this is giving you the pattern speeds. This is the bar starts at R0. It ends like this. This is the extension of the bar. The contrast giving the strength of the bar. And this is the spiral structure. This is plotted in logarithmic scale. So you see that we have a fast bar, slow spiral structure. It seems like there's another spiral structure right there. This is at later times. So this is the m equal 2 component, or 2-arm structure. Now, m equal 3 component, the bar is not there anymore. But it seems like you have two patterns, or at least one extended between the inner and outer inner resonances. We also, very interestingly, have an m equal 1, which means that the whole center is wobbling as it goes around. We have m equal 1 component and also m equal 4. So, a lot of patterns is going on. Just to zoom in here to show that this is at earlier times, later times, you see that the bar slows down. That's what you expect, because it gives ample momentum to the halo. As the bar slows down, the spiral structure slows down also. It seems like they're coupled. Okay? So that means that they're not really transient, but they can propagate for a long time if they're coupled like that. How can we see if they're coupled? Masset and Tager have shown that two waves can couple to a third one if you have a wave number m and a frequency w, such that you have these two patterns, the bar and the spiral, for example. You can either subtract them or add them, and at the same time, look at their frequency, subtract and add. And we have found out this makes sense for there's coupling between the bar, which is an n equal 2, and the n equal 1, coupling into an n equal 3 component. That's why we see an n equal 3 spiral, 3-arm spiral, because the bar couples with this wobbling in the central part. There's also coupling between the n equal 2 and n equal 4 spiral. So we have, essentially we have the bar, which is wobbling, that gives n equal 1. The bar is an n equal 2. There is an outer spiral moving slower than the bar, and an even outer spiral moving slower than everything else. And all of those seem to be coupled. And then, because they go through each other, they will constructively interfere and or destructively. You will get different variations with radius. Possibility for a 3-arm structure in the Milky Way.
Well, I understand, like, if I have a strong n equals 2 bar, right, why don't I just get a strong n equals 2 star strong? Why do I have to have a multiple waves on it? Down?
Yeah. Well, it seems like this 3-arm will come from this, the bar coupling with this wobbling, right? So you have something like that.
Yeah. What?
I'm sorry? I didn't get it. Right. The thing is that the inner spiral could be driven by the bar, but the outer one could exist on its own. So moving to the next part, small-scale phase space structure in the disk. This is the same galaxy we're looking at solar solar neighborhoods, there are different radii like this to see how structure varies as a function of azimuth and radius. This is in pi versus r plots. So you see these, that's how they show up, these neighborhoods. Very interestingly, on the arm, the high velocity dispersion, probably expect, in between the arms there's low velocity dispersion. This is UV. Wider means high velocity dispersion, right? So the sum is between spiral arms, and we're measuring this kind of velocity dispersion. That's on the arms. If you average over that azimuth, you expect higher than what's observed. UV plane in different positions. This is about the scale position of the sun. Here we're going to the center. You see that as we go to the center, of course, the thing is much hotter. But you have these gaps, very interestingly. Those are happening where you have change in the dominant wave. We have a different pattern appearing. So there's structure all over. If we get observations, we can get very good constraints on the non-axiomatic structure. Now, as a function of time, this is for particular radius near the sun. This here is angle with respect to the bar, and this is where we believe we are. And you can see there is this bimodality, which we expect in the solar neighborhood. That's the Hipparcos stream. This is for different times. And it seems like this is always there. With respect to the bar, this is always the same angle. Great here, there we go. This is the cartoon. Shows the Milky Way structure. We are located right here between these arms, just outside the strong arm. We pick similar positions from our simulations at different times, making plots. That seems like the Hipparcos. And here we see these three prominent clumps, which look very much like Hipparcos velocity distribution. This is for the first time, this is a self-consistent simulation which shows that we can reproduce the UV plane in this way. For challenges, uncertainty mechanisms, degeneracies, you can break those. We have observations all over the galaxy. Spiral structures are model, transient, or coupled. We still don't know how to distinguish between these. Nature of spiral structure in our galaxy, pattern, number of arms, lifetime, lack of consensus at this time. Migration, mixing, and heating depend on time and position. We still don't know how much we should expect from mergers. Star formation could be wave-driven versus localized bursts. That's because of this interference of the patterns with different radii. They have different strength of patterns, and that will trigger different kinds of star formation, different strength of star formation in function of radius. So star formation is not going to be smooth, right? And we need to understand the role of mergers in triggering spiral structure for ineffective heating and mixing. Conclusions. Now, the most important, I guess, is that galactic disks must be modeled as non-equilibrium systems. Since the solar neighborhood, for example, has only rotated 40 times since the galaxy formed. You don't expect that with an equilibrium configuration at this time. It's not like the solar system where you have units of orbits. This mixing, as I showed from resonance overlap, would be extremely efficient and thus very important in this evolution. I show also the bar can account for low velocity structure in the solar neighborhood velocity field. This would imply that the nuclear part is dynamically young. Structure and velocity distribution expected all over the galaxy would be related to changes in the dominant wave, to discontinuities in arms, or in the resonances. And wave at all radii may be coupled. Time-dependent models must be better explored. Precise measurements will be made as observations become more complicated. Thank you.
We have time for a few questions. So let me, what do you think the role of gas, like damping down for this particular
Cooling, so it's cooling the disk. For example, that antibody is very concentrated at the end that does not have a gas.
Yeah.
We get gas. Yeah, we would expect the spiral structure to be stronger than this. And not clear whether we'll have the same coupling, for example. That's something that, that, but not in Milky Way size.
So what do you think causes the difference?
Well, definitely get contribution from this mixing in the early stages.
Right.
So a very effective way is actually to do it. You expect that at high redshift to see very strong pumps in the gas, which has been shown, I believe it will know. There's a paper on that, it's very quickly, in just 1 week a year, you can create it with that. Both the voltage and thickness. So those pumps going around. And another thing would be, of course, the mergers once those perturbers get heat to this up to a certain level.
So in the solar neighborhood, what percentage of stars do you think could be radially migrated by different systems?
Well, that's the thing that you can't tell before you have average and you have accurate ages, right? According to
the age relation and then who is scattered.
right, but then I said that that's not true, probably because ages are very long. So if ages are wrong, everything will be scattered, right?
But
So we don't
let's
know.
say we take those data as real, what percentage do you think is
Right. Okay, so about 50%.
after starting from
Yeah.
after ages?
Very easy. Yeah.
It's significant amount.
Sorry?
It's a very significant amount.
Yeah.
Did that make this galaxy look bigger this time?
Sure, yeah. Which galaxy? What do you think?
Did that make this galaxy look bigger by a factor 2 compared to higher shift?
Oh, yeah, of course. So that's one implication that possibly, I was thinking, the fact that we can't, in cosmological simulations, we can't get this just because we don't have high enough resolution to develop strong bars and spirals as the voltage is forming. And you have a discrete component, but it's not extended enough. But if you have very strong bar and spiral, that thing will just, in half of the year, will expand this exponentially to what we do today. Right, now we're doing work with Cecilia's connectivity, which she does in Potsdam. She's working on this. No.
Any more questions? So if not, let's thank the speaker once again.